then they're sweet. All right, so we were talking about asymptotes, and we saw two things, two types. Horizontals, we just worry about as I get out toward infinity, what y values does my function get close to? Okay, that's an end behavior question. If we have up and up or down and down, it's easy because there's no horizontal asymptote in that situation. They have to settle on something. The vertical asymptotes, there are the vertical lines that no matter how close we get to it, I see my function either blows up to a positive infinity or it blows up to negative infinity. Blows down is really the language it should fit there, but it just doesn't feel right. It approaches positive or negative infinity. Now, as we go through here, it's fine and dandy. These things exist, horizontal and vertical. We're going to make sure that we can see that there is a really quick and easy way to deal with these. So let's go ahead and just dive right in. And here we go, finding asymptotes. And I'm trying to see, we have asymptotes. We'll call this little asterisk, finding asymptotes. Now, if you guys are interested, what we're doing right now is essentially calculus. We're not talking about it in the same context, but if you'd like to see a little bit of the calc notation while we are introduced to it, we can. If you say, nope, I'm good without seeing it written any other way, and we'll see it next year, I'm good with that also. Okay, for finding asymptotes, we're going to consider a single function. And we'll just start off by making sure that we have a clear understanding of where we're beginning. Consider a function, and it's going to be a rational function, where we'll call it f of x equals, just like before, some numerator piece over some denominator piece with no common factors. Now, we'll see what the common factors wind up doing for us. But right now, we're just saying that there's nothing that we can simplify out of this. Okay. No common factors. I don't know why I'm walking over here. Nobody's over there. We're just going to turn that off because it says my bulb is trying to die. But I don't believe it. Okay. So we're considering a function with no common factors. We have, I'll just put this, we have the following. Now, when you guys are thinking about this, we haven't done a full problem yet, but what seems harder, vertical asymptotes or horizontal in your head? Okay, anybody else agree with that? Like it's hit or miss, right? 6 or 7, if you will. Gosh, I'm on fire today. I'm in a terrible mood if you can't tell. Okay, we have the following. Turns out vertical asymptotes are way easier. So I'm going to change color when we do this. Let's talk about the vertical asymptote, which remember VA will always be my shorthand. The vertical asymptote, super easy. We'll just say x equals, and then I just need one quick thing, zeros of, what makes me blow up to infinity? A really small denominator or a really small numerator? So a small numerator goes to 0. But remember, vertical asymptotes shoot to positive or negative infinity. What I mean by that really small numerator denominator is if I was dividing, and I'm just going to do some numbers here. You don't need to write these, okay? If I take 1 divided by, give me a small number, like fairly close to 0. Give me closer to 0. 0.5. I'm going to write it as 1/2. What's 1 over 1/2?
2.
Okay, give me closer to 0 than 1/2. 1/4. What is it? 4? How about 1 over 1/100th?
100.
Sorry, 1 over 1/100th is 100. And I can see that as my denominator gets closer to 0 or smaller and smaller, the whole value blows up, right? If I divide by 1/10, it's big. Or 1/100th, it's bigger. Or 1/1000th, it's bigger still. So we'll just say vertical asymptotes, all we need is the zeros of d of x. These are the places that make us divide by 0, so they're undefined. They're outside of our domain. We can't use them. But it's also, as we get really close to that x value, it's what makes these things blow up to positive or negative infinity. Okay, these ones are easy. That's all we have to say about it. For the horizontal asymptotes, it's also easy with the understanding that if you were to make a note card and able to use a note card, this is probably something you would want on it. So check it out. We talk about the horizontal asymptotes, and before we can just say what they are, we will consider the degrees. And what I mean by that is we're going to consider the degree DEG is the degree of n, which I'm being kind of informal to save time. What is n? Numerator. And the degree, DEG, of the denominator, d. Okay. Now, we're going to see a few of these, and we can get some intuition for it, rather than just blindly giving you the rule. But if I'm comparing the degree, first thing, what is degree? What does that even mean?
The exponent.
The biggest power of x that we have. Okay, if I have a top and a bottom, right? Degree or denominator and numerator. Weird, numerator and denominator. And I'm comparing their degrees. There's only 3 possibilities whatsoever. Give me, if we were trying to compare them, d could be bigger, smaller, or equal to n. Are you guys cool with that? Now, there's no particular order that I'm doing these in. What do you want me to do for the first one? The degree of n, is it greater than d, equal to d, or less than d? So if the numerator is bigger, the degree of the numerator is bigger. Now, without going too crazy with it, I'm going to do a bunch of writing on the whiteboard, and I guess I'll just do it off on the side over here. If it's in the grass, it's just for class. So here's the grass that I'm referring to. Cool. All right, you do not have to sketch this, but give me any function of degree n. Like, what do you want the degree to be? What's your favorite number? Cool. So let's say that up top, and this is just us thinking, x cubed plus who cares because I'm only worried about the degree. Over, give me something smaller than this. 1, cool. So x plus dot dot, who cares? Which of these gets bigger faster, the numerator or the denominator? Like way faster, right? Because it's x cubed. Now, if I plug in 10, I can already tell it's 1,000 over 10. That's 100. If I plug in, I don't know, 100, and I'm going further to the right, I'm going to get 10,000 or 100,000, I'm not sure, over 100, and that's a bigger number. Am I ever going to stop getting bigger and bigger and bigger? No, which means this function will never keep going up and up and up or down and down and down. If this happens, super easy, this implies if the numerator has a larger degree, no horizontal asymptote. And if it didn't click what I was saying there, because it can be hard to talk about that math, I'm going to go to Desmos real quick, and I'll show you a function and multiple functions where the degree of the numerator is bigger. Okay, so let's go over here. Don't read my emails. I say that, but you could go back and pause on the video. Good luck. I don't have any interesting emails. All right, let's see. X to the 4th plus 3x plus 1 divided by x squared. Okay, now notice this graph, whatever, it's fine and dandy. Yep, so I don't really care about the graph itself, but what I do notice is as I move further to the right, what does the y value do? Forever. And if I zoom out, it's just going to make it look like a straight line. But does that seem to agree with what we just wrote? There is no horizontal asymptote. Now in the middle, remember we don't care, it's only about the end behavior. As I move farther and farther left, does it keep increasing as well? So it seems as though I'm increasing without bound. I'm not getting close to some y value. There's no asymptote. Okay, there's our first possibility. What's another possibility? Equal. So I am going to make sure that this looks like this so I don't confuse it with a negative at some point. Let's try equal. Now this one's awesome. If we take the degree of the numerator n, and we set it equal to the degree of the denominator d. And this time we will go over to Desmos because I want you guys to help me make sense of this. N and d are equal. Okay. In this situation, I'm going to play around with some numbers here. And I'm going to move this so that you guys can see the whole screen. And we're going to work with some nice functions. What do you want the numerator to be? Lots of strong opinions there. 2x cubed plus 4. Beautiful. Now, if I want it to be equal, I just need x cubed, right? So let's say it's negative x cubed, for example. I will reset this because you can't tell anything that's going on, but I'm going to zoom in. Now, the degree of the numerator is 3. The degree of the denominator is 3 as well. Do you guys see a horizontal asymptote here? A line that I get arbitrarily close to? Okay. What does it happen to be? Can you tell? So here I am.
2?
It certainly looks like it's not 2. Looks like -2. Like your 2 was good, but it's -2, right? How about as I go further to the left as I approach negative infinity? It's -2 again. Okay, this one, it's not going to like this, but I'm just going to put it here. You guys told me that this one had a horizontal asymptote at y equals -2. Okay, we'll just keep that there. Let's get another one. Maybe that was just coincidental. Let's do x to the 4th, and I'll just do something that I know doesn't factor. Let's divide this by 2x to the 4th. Okay, this time, same thing. Degree of the numerator is 4, degree of denominator is 4. If I track this out, what does it seem like my y value is getting close to as I go out toward infinity? 1/2, 0.5, and eventually it'll say 0.5, but it's just a rounding issue. What about as I go really far to the left? Is it negative? Is this point above or below the line? So it's still 0.5. Now I'm going to write this differently. Y equals 0.5. You know what? I'm just going to write it like this. Before I graph this last one, and I'm just going to pause it now, anybody think they might see a trend happening? Okay, don't shout it out yet, in case you do. I just want to try x squared. We'll do 3x squared plus 5 over x squared. Turn with your neighbor. I'm going to give you like 15 seconds. Hopefully there's a pattern emerging, but if not, that's okay. 15 seconds, I want you to tell me where is the horizontal asymptote, because I know where it'll be. Redmond, I heard you say it immediately, and that's awesome. What do you notice is happening? The leading coefficient. So if we check here just to kind of backtrack, a 2 and a -1 is -2 if you divide them. 1 and 2 is 1/2. Where should the asymptote be on this one? Is it? Am I getting really close to y equals 3? From both sides? Hey, fantastic. It is 3. Nice job, Red. Nice job, everybody who noticed that, but Red's the first one that I heard. How could we write that then? The horizontal asymptote, and I'm going to be crazy about this just so you know. Horizontal asymptote at y equals, how would you write this? Love it. Now, just to be really clear, what is LC short for? So if I say the leading coefficient in n of x, I'm going to use brackets because I think they look a little nicer, over the leading coefficient of d of x. If they're equal, it's that easy. Okay, there's one more possibility. N is larger, n is equal, or n is less than. So degree of the numerator is less than the degree of the denominator. Now, we'll see there's one more type of asymptote that we'll have to consider, and we may use similar language, but I'm okay with this for now. Less than. In this situation, what gets bigger faster, the numerator or the denominator? So I might have heard denumerator there, and I'm not quite sure how to make sense of that. The denominator. If we have x squared plus 1 over 5x to the, we'll be it obnoxious, 5th. The denominator gets huge way faster, right? Now, pick a really, really big number. This is way, 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 way bigger than the numerator. So, like, pick a big number in your head, relatively big. Give me a number. I don't care what it is. 250? Cool. 250 over 20 trillion. I picked a much bigger number that got bigger way faster. 250 over 20 trillion. It's almost what? If I give you 250 trillionths of a dollar, are you bummed or psyched?
Bummed.
Like it's, there you go. You just got it, right? It's essentially what? 0 or nothing. Now, let's just do a quick check here. And we don't have to pick like obnoxiously large numbers like that, but it does make it a little bit easier. You guys said 0. Let's verify that. Let's do x squared plus 1. And I'm only using this example over and over because I know it doesn't factor, so I don't have to worry about simplifying. Give me something bigger than x squared. Okay, that's a lame one, but I'm going to do x to the 4th. Cool. As I get really close, what does it look like the y value we're approaching is? 0. So check it out. If it happens like this, then the horizontal asymptote is going to be found at the line y equals 0. These are the three possibilities, and only these three. Now, we get to put all of this together along with all the factoring stuff. Now, we're going to be sketching some functions here, and they can be intimidating. Can you guys factor? And what do we use factoring for? We use factoring to find the zeros. So if I had the zeros and the asymptotes, do you think we could sketch the graph pretty well? You might believe me, and you might expect that it's coming as a yes, but let's do that. We're going to put everything together at this point. Now, would you guys like to get a history fact real quick? Yeah. All right. Cool. We're going to put all the pieces together right now, and you guys are going to help. Sweet. Let's sketch a function. So here we go. This is going to be essentially a big example, but we'll make sure that we have them. Sketching f of x equals n of x over d of x. Now, I have this lovely, like, 7-step process, and that's a lot of steps. I don't always do them in the same order. Let's check one out. We'll work one together, and then we'll refine and say, hey, what were the steps that we did? And again, not in a particular order. So we're going to use all the key features. So really all that we truly need, we're going to find a few intercepts, x and y. We're going to find some asymptotes, and that's essentially it, realistically. Let's dive in. Here we go. On example A, let's sketch the following. I want us to graph. It's a lovely rational function. So we get f of x is defined to be x squared plus x minus 2 in the numerator. X squared plus x minus 2. And we're going to divide this by x squared minus x minus 6. There is a ton of information hiding in here. Okay. For this, again, there's no real specific do this, then this, then this. But I do know that there's a ton of stuff that we can draw out of it, and we'll see if we can make sense of it. A fraction, like let me rephrase this. There's a ton of really handy stuff that we can get. Key characteristics. When I talk about those, do you guys know what I'm referring to? What are some of the important things on a function or a graph that we might have talked about before? Intercepts. Do you guys want to find intercepts first? Okay. Now, when you say intercept, do you mean x or y? Okay, let's start with the x-intercept. Now, there's no real specific order to this, just so you guys know. Okay, I'm going to do a little bit more annotating in this example. Rather than defining it, we'll just do them all at the same time. So I'm fine with this. No particular order. Find x-intercepts, or the roots is the easier way to write this, of f of x by solving, and I'm going to pause right here because I want you guys to help me think this out. If I'm looking for the x-intercept, it's 0, right? That's what it spits out at me. When is a fraction equal to 0? When what part of it is 0? When is a fraction equal to 0? Something over something equals 0 when what part of it is 0? If the denominator is 0, try to divide by 0. Does it work?
Oh, no.
It's undefined there. So let's just see that. Do we all agree that a fraction is 0 when the numerator is 0? Because it's 0 over something and it's 0. Okay. So if we want to find the roots of this, we simply solve the equation for the zeros of the numerator. Now specifically, that's n of x equals 0. Okay. Now here's like the general rule. I'm going to switch this green color while we work it, and let's do that same step. What's my numerator?
X squared plus x minus 2.
Okay, we need to set this equal to 0 and solve it using our F word. Factor. Almost went a bad joke there, but that's okay. I don't remember how to factor. That's super embarrassing. There's no GCF. I agree. It does suck. No GCF. What should I check next? Did I give you guys a factoring list?
Yeah.
Okay.
You could do the scooping thing.
Hey, we'll get there. I'm going to check. There's no binomial, right? And you guys are, I think, probably okay with that. You okay?
Yeah.
Okay. So check it out. Leading coefficient's 1. That's pretty handy. Why?
Feels trick.
Okay. Can you guys think of factors of -2 that add up to 1?
2 negative 1.
So 2 and -1. So that means I know that this is x plus 2 and x minus 1. We're just using a shortcut for factoring, equals 0. What are the roots here of our function then? So f of x has x-intercepts or roots, and I'm going to put all this information like over here, and we'll compile it as we go. I lied. I'll do it at the end. Roots at x equals -2 and 1. Now, normally what I would do in this problem, like I'm fine starting here. If we've already factored this, and I can see it's factored, here in a minute we'll be able to write both of them to see if anything divides out because we want them to not have a common factor. But for now I'm content with this. What if I wanted the other intercept? Yeah, how would you find the y-intercept? Say it one more time. So we don't have to, so that would do the same thing here because I would just multiply each side by this and I just wind up with this anyway. But what if we think about the y-intercept, it's along the y-axis, right? And what's the x value there all the time? It's at 0, right? So I think we can get the y-intercept by finding f of, what x value did you say the y-intercept happens at? 0. I think I can just evaluate f of 0. When x is 0, what's the value of my function? That's going to give me 0, comma, whatever y is. Now, I don't think it's super ugly. Can we all agree it's 1/3?
Yes.
Because 0 plus 0 minus 2, -2 over -6. So I just found the y-intercepts at the point 0, comma, 1/3. Yes, ma'am.
Can you explain one more time how you got 1/3?
Yeah. Do you agree that, like, help me plug in here. What's 0 squared? Because I'm evaluating when x is 0. 0 squared is 0 plus 0 minus 2. So that's -2 over 0 plus, or minus 0, minus 6. Yep, and there it is. Thank you for asking. Okay, so now we have x and y intercepts. Yes, we haven't gotten there. We will. We will. In fact, we'll do it right this second. Weisha asks about the roots of the denominator. Well, if I found the zeros of the denominator, that's where it makes me do what again? If the denominator is 0, it tries to make me divide by 0, right? And when I try to divide by 0, as I get really close, I see that infinity idea showing up. So I love that idea, but what do we say we find at the zeros of the denominator? Yeah, let's find them. Let's find the vertical asymptote at x equals roots of denominator. And I'm going to say roots of d of x. Now we could do the same thing, set d of x equal to 0, all that good stuff. But let's check it out. I want you guys to do this one for me. Find me the roots of the denominator. I'm going to pause it. So at this point, we almost have enough information. There's a vertical line that I'll never touch at -2, and there's a vertical line that I'll never touch at x equals 3. These are the zeros of the denominator. Now, realistically, when I'm doing these problems, like we're just going through with whatever key features you guys give me to begin with. I hate that I didn't undo those, so I'm going to rewrite that because that's going to bug the heck out of me. X squared, sorry about that, plus x minus 2 over x squared minus x minus 6. Now, realistically, the very first thing that I do before I even start doing all this, because I know we're going to use it, is I factor this down first. Now, the good news is that we don't have to do anything different. Do we know how the numerator factored? That was x plus 2 and x minus 1, right? Because we already have it written down. And I'm doing this only so I can check to see if anything divides out. Hey. Well, that's weird. Okay. Now, we're going to have to come back and change a little part of our answer, and that's okay. Like, we'll deal with it. I've written the factored form. I would normally begin here, but it's okay. Is there any other information that we've talked about? So we've got the roots. We got y-intercept. We have vertical asymptotes. If only there was something else that we could use. So end behavior, I agree, but that's kind of like asking about the... The horizontal asymptotes. So, HA, like, end behavior is a great thought there, and I agree with you completely, but let's just call them the horizontal asymptotes, since that's what it is. Okay, so to check this, all I need to be able to do is check the degrees. What's this degree? Ooh, you say 1 because I'm pointing at what would be the leading coefficient. What's the degree of the numerator, rather? 2, the degree of the denominator. So if we look at the horizontal asymptotes, the degrees are equal, and you can write this if you want. You don't have to. Degree n equals degree of d, which means it's simply the line y equals
0.
y. I don't agree.
No, wait. No, 1 over 1.
1, because 1 over 1 for the leading coefficients.
Did you add them?
You just the ratio of the leading coefficients. So if this were 1 over 2, it'd be 1/2. Okay. Kind of divide, but you don't need the actual quotient. Okay. From this, there's only one little weird part, and it doesn't fit in nicely here. We made the comment that when we were looking at the asymptotes and stuff, and we're going to cross off a couple little things here, 2 little things. Was there anything that would simplify out of my function to begin with? What would fall out? X plus 2 over x plus 2. Now, I want you to be able to see it. Don't just blindly erase it. But we're going to do this so I can see this. And then I'm going to make a note leading to this. Okay. If we are able to remove this, which is what just happened. We removed this factor. This is a hole in our graph. Now, I heard Dolan say, I think. Do you guys remember dealing with holes in graphs at some point? Okay. Can you tell me where the hole happened? At -2? At x equals -2. And in case we want it, and it's always good to have, how did you know it was -2? Good. So I'm just going to say the factor, or the root from the factor we divided. The root from factor. And I'm going to change the language that we removed is what I'm going to say. Okay. Everybody okay with that? The root from the factor we removed. Okay. So we need to change one little piece of this then. It doesn't change this. That's fine. Except, gosh, -2 showed up there. I can't use it anymore. It's a hole. And then -2 is here also. So I just can't use them because there's a hole in my graph right there. Now, maybe the vertical asymptote will be okay, but we'll check it. I am going to actually cross it off for now, and we'll see why not. Okay, do we have enough to graph, you think? Does it feel like we've done anything in preparation for actually graphing, other than the fact that I've told you we have? We found a ton of points. Let's check some stuff. Let's put all this together. And then we'll go over the quiz, and then we'll have one more, I think. How's your work week looking? How's your week? Do you guys are you busy right now? It's the end of the quarter. If we have like a whole class session tomorrow to talk and work, will we take advantage of it? Okay, cool. So let's check this out. I just want to identify some of the stuff that we have already. Now this graph, there's cooler ones out there, but that's okay. Check it out. I'm only going to plot the stuff that we've seen, and I'm not going to be super crazy with this. I know that I have to go out to 3 because there's a vertical asymptote there. So anytime that I have a vertical asymptote, I'm going to try to go, I want to see both sides of it. So I don't know where it is, but we'll go 1, 2, 3. I'm fine with that. 3, 4, 5, and I'll go out to 5, and I'll try to keep this. I haven't decided yet, but I can already tell 1/3. So I'm going to make that my 1. Now, just talking through it a little bit. Out to 5 because I know I'm going to have a vertical asymptote or something weird here. that I want to be able to see. So I'm going to make sure I can see both sides of it. Then why do I only go up to 1 here? Why is this a change of 1 on the x-axis, but this is my change of 1 here?
Approaching thing.
Maybe the approaching. What did we say my y-intercept was?
1/3.
1/3. If I made it this size, it's going to just be tiny. I just did this so I can see that 1/3 easily. Okay, so let's start putting on some other pieces then. Where are the roots? There's only one of them apparently, because the other one fell out. Where's the root?
1.
At 1. So I will use a lovely, I don't know, this beige brown. So here's the x-intercept at x equals 1. Cool. Anything else we could add? Okay, so I'll add the y-intercept at 1/3. So would you believe it if I said here's 1/3? Now, we are so close to seeing some really important stuff, but we'll deal with it. Do we have any vertical asymptote? It's at 3, right? So I like to use a dashed line. I'm going to make mine purple. You guys can take colored pencils or use colored pencils in class whenever you want. Okay. Okay, this pink line is going to be on my vertical asymptote. Am I ever going to touch it? No, don't touch it. Okay, never. Anything else I can put on here?
Horizontal.
Hey, there's a horizontal asymptote, and this one's going to be strange. It's at y equals 1, right? So it's right here. Just kidding, we'll try that again. It's right here. Now, as we go through this, notice, what did I say about the horizontal asymptote? Don't do what? Don't touch it. Don't even think about it. But here's the deal. The horizontal one, you can touch it. I'm fine with that. Because we only care about where. The horizontal asymptote, Addison tried to tell me a different word for it, and I corrected and said, no, let's call it the horizontal asymptote, but your word was correct. End. The ends are at infinity. This is only telling me what's happening at infinity. I don't care about what goes on in the middle. We can cross it. All right. Anything else?
What's the point of the horizontal asymptote if you can cross it?
So, because it's, we'll get there. You'll see that here in a second. Okay. Well, let's try some stuff. Do you think I have enough to actually graph this right now? I think so too. Okay. Couple things that we're going to put together, some big pieces. Did this root right here, how many times did it show up? Like when we factored, there's only one factor that led to that, right? Its multiplicity is 1. Why do I care? It crosses the x-axis there, which means it was positive, I can tell that, and it goes down. Is there any chance that it comes back up like this? Why not? It's odd. We would have found another root here if it crossed again. Now, just from these two, knowing that this is the only place my graph will ever cross the x-axis, I think pretty confidently that I know that the left side of this does something like this. Now, Addison, you asked, why do we care if we can cross it? Because as I get further away, I know that I get really close to it, and I mellow out. And it would have been okay. We'll see functions that could do something like this. I don't think this one does, but it could cross, but it would still level out there. Now, I don't think it's going to cross, so I'm just going to draw it getting really, really close, and we're going to come into right here. Now, remind me again what happens here. It crosses, and at 2, or at -2, which I didn't even put it, what should I have in my graph? There should be an open circle at -2. So I'm just going to backtrack and add those on, -1, -2. This should be an open point right here. I'm going to make it a nicer open point. Now, never trust Desmos. Just like realistically, you should trust Desmos as long as you type it in correctly. But computers don't see the hole because holes are infinitely small. It's a single point. You will never see it on the graph on Desmos. Never. It'll just look like a solid line. Okay, so we have that, and then it crosses. Did we take any time to get points in here? No, but I know it crosses. It's not going to cross again. What's its only option? It goes down, it decreases without bound. It must look like this. Okay. There's the first half of our graph. There's no other option. It can't turn around. Now, we didn't get any points on the other side, right? We didn't plug in 4 or 5 or anything like that. Let's think it out. I'm only seeing two possible regions from which it could live. And you don't have to color this, but it could either be up here or it could be in here, right? Those are like, it's going to be stuck between those essentially. How do I know it's not the yellow one? So maybe the asymptote. I don't think it would have to cross the asymptote, but it would cross something. It would cross the x-axis. But if it crossed the x-axis, we would have found a what? There's no x-intercept. Like there's not one over there. It can't be yellow. It would have to cross. So if it's not in that yellow region, it must be in this bronze region, rust, red. I don't know what color it is. It must be up here. Now, if I wanted a better picture, could I get a point real quick? I could, and I'll just check real quickly. If I plug in a 4, 4 minus 1 is 3 over 4 minus 3 is 1. So at 4, it's a value of 3, so it's way up here already. Now, I'm not going to take the time to actually do that, but if I know it's stuck up here, it can't cross the asymptote, it's going to have to do something like this. Now, my graph isn't perfect, but that's okay. All right. Tomorrow, we'll do another icky one together. But for now, this stuff seem okay, seem terrible. Where would you put it? Now, we could make our numerator uglier, make you use a PQ list to find the roots, like there's bless you. There's an easy extension to make these problems seem harder. I don't know that the concept changes. It's just more involved with the work within. Okay, so we gonna pause here.